So let's see. We were talking about resolutions by pictures, right? And we said that once you have a labeled polyhedral complex that we called X, so let me remind you what that is. So we have a polyhedral complex, meaning a bunch of nice polyhedra glued together, perhaps. And maybe this is an example that we can talk about. And I hope you can see the labels. So this is an octahedron, and when I talk about the complex, I'm considering all the faces of this octahedron. So the octahedron itself is one of the faces. Each one of its triangles is one of the faces, like that. Okay? Now, remember what we do is that we label each vertex by a monomial. And here, just to make the notation a little bit cleaner, I'm just denoting it by 0, 1 vectors. But for example, when we see 1, 0, 0, 1, really we're thinking about the monomial AD. Okay? And then remember that the way this goes is that once you label the vertices, then that immediately gives you a labeling of all the other faces. Okay? And the other faces are given by the least common multiple of what you see on their vertices. Okay? So for example, just to label a couple of things here, if we label, I don't know, maybe this bottom face, this face right here, well, I guess the labels are 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, and the LCM of those things is 1, 1, 1, 0. If we label the neighbor that's right above it, this one, then that's going to get a label, and that label is called here the LCM of 1, 0, 0, 1, 1, 0, 1, 0, and 1, 1, 0, 0 is 1, 1, 1, 1. Okay. And we label the edges also. So for example, there's a label on this edge, which would be 1, 1, 0, 1, right? Etc. So the labeled complex is all of this stuff. Question?
Is it possible to have two faces with the same wavelength?
That's a very good point, and it actually happens right here. For example, there are several faces that are labeled 1, 1, 1, 1. Can you tell me another one? I have no idea what you're pointing to, but yeah, it's a good description. The bottom one that's facing you, right? This one. So this guy also has the label 1, 1, 1, 1. And this is the first time that we see that things get repeated labels. And what that means is that for the first time we're actually going to see Betti numbers that are higher than 1. I think you guys were always confused that the Betti numbers were always 0 or 1. But that's no longer going to be the case. So this is the label cell complex. From it, we get a cellular free complex, which we wrote out. Is basically the thing that you would write out for homology for this thing, except that you put the labels on. Okay? And we said that this thing is a free resolution. So it's a cellular resolution for R mod the ideal generated by the vertices. If and only if for all vectors b n to the n, the subcomplex x sub less than or equal to b is acyclic. And this consists of all the faces with labels less than or equal to b component-wise. Okay. And so we said that once we have a picture like this, it's very easy to write out, well, first of all, this resolution that I'm talking about. And second of all, you can get the Hilbert series right away. That's what we proved last time. Okay. Now, what I want to do today is talk about how you can also get the Betti numbers out of this. And so, first I'll state the theorem, which is very explicit. By the way, it might be worth it for you to think about. Well, actually, maybe before I state the theorem, what I'll do is just write out the cellular free complex in this case, so that we have something concrete to look at during all of this. Okay? So how does this go? Well, this is X. Okay. So what does this cellular free complex look like? What we do is that we first put a bunch of copies of the ring, one for each full dimensional thing. So here we live in 3 dimensions, and there's only one 3-dimensional piece. Okay. Then we put the 2-dimensional pieces, and in this case there are 8 2-dimensional pieces. Did I draw this, by the way, last time, or did I do a different example? Something different? Okay, so let's do this one very carefully then. So we have 8 2-dimensional faces. Okay. Then after that go the edges. So we have to figure out how many edges there are, and there's 4 coming out of the top, 4 coming out of the bottom, and 4 around the equator. So there's 12 edges. Okay. And then how many vertices? There are 6 vertices. And then the 0-dimensional face, right? And then R mod I, and then 0. Okay. And I actually need to uncrowd this a little bit, so instead of resolving R mod I, let me resolve I. And remember that the only thing I need to do is just cut out this R, and I'll get a resolution of I. Okay. So this is a resolution. Well, this is the cellular free complex. Okay? But the question is whether it's a resolution. And in order to know that, we need to know whether these x sub less than or equal to b are acyclic. But actually, I'm not telling you all the information yet, because to give you the cellular free complex, I have to give you this, but I also have to give you the gradings. Right? We have to grade everything. So for example, what are the gradients of these 6 pieces? Well, the gradients are given by the names of the vertices, right? And these are, the way that I labeled it, it's every 4 tuple that has exactly 2 1s. So maybe, so let's do it like this. So 1 1 0 0, 1 0 1 0, 1 0 0 1, 0 1 1 0, 0 1 0 1, 0 0 1 1. Okay. Then I have to label the edges. Okay. So what kinds of labels can I get? Well, you see, this guy gets a label of 1 1 0 1, right? Do you see anything else that has a label of 1 1 0 1? If you stare at this long enough, you're going to see that this is 1 1 0 1, and this is also 1 1 0 1, and this is also 1 1 0 1. And maybe put those in a different color so you can tell it apart. This is why I brought lots of colors today. So this edge right here is 1 1 0 1. This edge right here is also 1 1 0 1, and this one is also 1 1 0 1. Okay. And by symmetry, we can tell what everything else is, right? Because there's 3 copies of this guy, but if this guy is here, then by the symmetry of everything, basically we need to have the following. We need to have 3 times 1 1 1 0, then 3 times 1 1 0 1. Then 3 times 1 0 1 1, and 3 times 0 1 1 1. Okay. So that's what that looks like. Next, we have to figure out how to label the two-dimensional faces. And again, because I have a 1, 1, 1, 0, by symmetry, I know that I'm going to have a 1, 1, 0, 1, a 1, 0, 1, 1, and a 0, 1, 1, 1. Okay? And if you kind of do this carefully, you'll see that all the other guys get the label 1, 1, 1, 1. There's 4 faces that get 1, 1, 1, 1. Actually, if you happen to have taken a class in tropical geometry and Bergman complexes, then these 1, 1, 1, 1s are exactly the things that contribute to the Bergman complex of this matroid, whatever that means. But that's not too important for us here. Finally, R to the 1 is the label of the full thing, which is 1, 1, 1, 1. So this is really what the complex looks like, and remember that there's some monomial matrices here, which are basically these 1 minus 1 matrices that give you the boundaries of things. Okay. And so remember that we want to know if this is a resolution. So what we do is for every single vector b, we have to look at the things that are less than or equal to b, look at the subcomplex, and make sure there's no holes. So maybe we can just do that for one example, just as a sanity check. So what is x sub less than or equal to 1, 1, 1, 0? Well, let's do 1, 1, 0, 1 since we have a lot of it already. What are the labels that are less than or equal to 1, 1, 0, 1? Well, we certainly have those 3 edges that we talked about. Okay. Now, if you think about what the label of that face is also labeled 1, 1, 0, 1. Okay. And then, of course, the vertices have to be less than or equal to 1, 1, 0, 1. There's something implicit here, which is that, as you go from bigger dimensional things to lower dimensional things, the labels can only get smaller, right? Because you're taking, if you go from the triangle, which is the LCM of 3 things, and you go to its edge, which is the LCM of 2 of them, your label either stayed the same or got smaller. And that means that if a triangle is part of this, then all of its faces are going to be part of this. So this is in its own right a polyhedral complex. And if you look at this carefully, you'll see that there's nothing else. So this is the subcomplex, and this has no homology. And of course, we have to do this for every single b. Okay. And so, I'll just give it away that this does work. So this is a cellular resolution. A cellular resolution of R mod. Well, I guess here we just chose the ideal. So the ideal looks like AB, AC, AD, BC, BD, CD. Right? Those are the monomials corresponding to the 6 vertices. Okay. And now we can, well, by the recipe that I gave you last time, you can immediately write out the Hilbert series of this guy. Okay, but there's an issue that's important here, which is that here I'm saying that this is a resolution, but I'm not saying that it's minimal. Okay. Now remember, what are these Betti numbers? The Betti numbers basically tell you what are the degrees that you see here. And if you looked at this resolution, you might be led to think that the Betti number, let's see, 1, 2, 3, comma, 1, 1, 1, 1. You might. What does this mean? It means you go to the 3rd step and see how many 1, 1, 1, 1s you see, and you might be led to think that this is 4. So hopefully now finally you see a little bit better what these Betti numbers would mean, because in general you might have repeated degrees here, and the Betti number tells you in the 3rd step how many times do I have this degree. Actually, I need to just say one thing, which is that this is not the third step, it's the second step. Because remember, we start at 0. 0, 1, 2. So if we look at this, we might be led to think that this is 4, but the thing is, we don't know this is a minimal free resolution. And if it's not minimal, then there might be extra stuff. Okay? We don't know since is this minimal? We don't know. Probably not. In general, it's not. And so that means that this answer might be wrong. So how do we get the right answer? Okay. This is what the next theorem says. If X supports a cellular free resolution of R mod I, then the Betti numbers of I can be computed from X in the following way. They are the dimensions of the homologies so this Betti number is going to be the dimension of this subcomplex. The dimension of the I minus first homology of this subcomplex. Okay? So once again, a beautiful theorem that tells you that this kind of subtle algebraic number that is hard to compute in general, if you have a picture like this, then it reduces to topology. It tells you, now instead of computing x less than or equal to b, you compute the things that are only less than b. And you find the homology of that. And whatever that homology is your Betti number. Okay? So let's do that in this example. We want to know what the Betti number 2, 1, 1, 1, 1 is. We guess it might be 4. We might be wrong. Okay? So to be right, to be sure that we know the answer, well, fortunately, we already have a cellular free resolution of this thing. And so all we need to do is look at, it's kind of like this guy, but we just throw out the things that have label equal to 1, 1, 0, 1. Sorry. Here I want 1, 1. Maybe let's do an easier example first. Okay? And then we'll do this one. So let's say first that I want to know the Betti number 1, 1, 1, 1, 0. Okay? Again, according to this, what would you guess that it would be? If this was minimal, then we would have to see how many times you have 1, 1, 1, 0 in this first entry. We have it 3 times, so we might guess that the answer is 3. Okay, but that depends whether, it might be or not. To know that, what we need to do is not consider the things less than or equal to 1, 1, 0, 1, but the ones that are strictly less than 1, 1, 0, 1. So what you do is you just take this guy and you throw out the things that have label equal to 1, 1, 0, 1, and you keep only the things that are strictly smaller.
1, 1, 0, 1 or 1, 1, 1, 0?
1, thank you. 1, 1, 0, 1. 1, 1, 0, 1. Again, by symmetry, I'm going to get the same answer, but let's be consistent. So 1, 1, 0, 1. So I take this picture and I look only at the things that have label 1, 1, 0, 1, label less than that. And we said that the 3 edges have label 1, 1, 0, 1. The triangle has label 1, 1, 0, 1. And so those guys don't get to live here. Only the 3 vertices get to live here. And so the subcomplex just consists of 3 vertices, and then this stuff is gone. Okay. And what I need to do, so to get the right answer, I need to get the 0 homology, the dimension of the zero homology of this thing, right? Which, do you remember how to do this? So basically, this gives me one hole, and this gives me another hole. But then this third hole is kind of a combination of the other two. In general, the zero homology number is just the number of connected components minus 1. So this is actually 2. It's not 3. And that tells you right away that this was not a free resolution, was not a minimal resolution. Okay? The number is 2. Okay? So let's do this one now to do another example. So the Betti number 2, 1, 1, 1, 1. Okay? So what are the faces that have label less than 1, 1, 1, 1? Well, maybe it's easier if I ask you what are the labels that have, what are the 1, 1, 1, 1 labels, and let's throw them out, and we'll keep everything else. Okay? So for example, this guy is 1, 1, 1, 1, and we should throw it out. And there's supposed to be 3 more. Do you see them? So, yeah. Well, I'll tell you what they are. So it's a matter of staring at this long enough. So it's this one, and then the one opposite to it, and then the 2 down here, kind of like this. In other words, the ones that I get to keep are it's basically every other face. Okay? This is gonna get tricky to draw, but basically it's those 2 guys, and then this back face, and then this front face. Okay, so it's kind of like what? It's like this and like this. I don't know if that helps at all, but and we need to figure out what is the first homology of this thing. Okay, and we have to do this a little bit carefully, but remember that you're allowed to deform these things into a shape that you like. Okay, and what you can do is that you can take each one of these triangles and kind of deform it into its center. Okay? So that the picture that you get just looks like the 4 centers of these guys, and then they're all connected to each other. I'm kind of taking these 2 triangles and then just kind of collapsing each triangle into its center, and then keeping the path between them because I need to connect them. This is a homotopy, so they have the same homology, and we know what the homology of this thing is because it's a simplex. We need the 2-dimensional holes, and basically they kind of correspond to the 4 faces of the tetrahedron, but one of them is a combination of the other 3. So this is 3. Okay. Again, how am I doing this? Well, I have some experience with algebraic topology, so I'm good at kind of deforming things, and I kind of know the homology of some of the basic shapes. Okay. But another way to do it is, well, you guys know that you do this chain complex and you do these computations. Okay. But anyway, so the point is that to compute the algebraic invariant, you just compute the topology of these things. That's how it goes. So this is the dimension of the first homology of the things less than 1, 1, 1, 1, and that's 3. Okay. So that's how this works. So are there any questions about the statement of this theorem? So what I'm going to do for the rest of the class is give you an idea of how this theorem is proved. And again, I think it's clearest if I just do this in an example which you will see generalizes. Okay. And let's see. Let's say that we want to do this for that example and for that B that I've talked about a couple of times. So B is, what did I say? 1, 1, what is it? 1, 1, 0, 1? I can't see. This is what you see over there. Okay. So, well, we have to go back and remember this theorem that we proved a while ago, which was the following, that the Betti numbers were given by the dimensions of these Tor things. So I'll remind you how that went. This is the dimension over my field of the Tor, the ith Tor, my ideal with the field in degree B. Okay. So that was kind of a long equation. What did it mean? Remember that what this Tor means is that you take a free resolution. So it's a Tor of two things. And it basically, Tor we said was about torsion. And it basically tells you, okay, let's say that you know how to do a free resolution of I. Now what happens if you tensor that thing with F? And so that's what we're going to do. So we know how to resolve I, okay? Because it's this thing. So this is the free resolution. This is the free resolution of I, okay? And now I need to tensor that with F. Which, if you go back and remember how this went, tensoring with F makes your life simpler because all it does is, we said that whenever you tensor the ring with the ground field, you just get the ground field. And so we got basically the same thing, except that instead of copies of the ring, we got copies of the field. And if the copies of the ring were shifted by degrees, then the copies of the field are also shifted by degrees. So that means that this complex that I want is basically this thing with the same shifts as before. Now, what is Tor? Tor is the homology of this complex as opposed to this complex. We're assuming that this complex has no homology, that it's exact when it resolves our ideal. But after we tensored it with F, we probably created some homology, and that's what we need to know. Okay? So we need to know what happened in degree B. Okay? So here's what happened in general, but what happens when we look at degree B. So let me change to a different color, and B is 1, 1, 0, 1. Okay? What we need to know is, we need to know in each one of these things, where do I have things of degree 1, 1, 0, 1? Okay? So I know, for example, that here I have a copy of my field in degree 1, 1, 1, 1. So there's nothing of degree 1, 1, 0, 1 there, which means that this disappears. Okay? Because this thing is not of degree 1, 1, 0, 1. Okay. Here, you'll see that the only thing of degree 1, 1, 0, 1 is this one, and everything else disappears. Okay. And so all I get is f to the 1. Now here, Again, all of these guys disappear, but these guys get to stay, and these guys disappear. So I get 3 guys here. Now, what about here? This is where it gets a little bit trickier, because in what we were doing earlier, if we look at the free resolution Fx, and if we look at the ring graded at 1, 1, 0, 0, the ring does have an element of degree 1, 1, 0, 1, which is D. Right? So here we had something of degree 1, 1, 0, 1. But here we have a field. We have a field shifted by 1, 1, 0, 0. And in a field, everything is a scalar. So everything is a constant and has degree 0 plus whatever the shift is. Okay? So that means that in none of these degrees do I have anything of degree 1, 1, 0, 1, and all of this stuff disappears. Okay. And this guy, I forgot to tell you that it's in degree 0, 0, 0, 0, and so it also disappears. Okay. So it was f to the 1, but now it becomes f to the 0. Okay. So what is it that I want to say then? I want to say that when I do this, this equals, and you'll see in a second why I'm putting this in quotation marks, this equals basically what happens, it equals the homology of this thing, right? And what am I doing here? What I'm doing here is that I'm throwing out all the faces that don't have label 1, 1, 0, 1. And I keep only the faces that have degree equal to 1, 1, 0, 1. Okay? So this should be equal to the dimension of the homology of the things that have label equal to 1, 1, 0, 1. Okay. So this is kind of what I proved. But there's a subtlety here. Does anybody see what the problem is here? I think it's hard to see unless we do an example. So since we're so happy with this 1, 1, 0, 1, let's do it here. So maybe let's draw the 3 of them. X less than 1, 1, 0, 1, x less than or equal to 1, 1, 0, 1. We said that was this triangle. Okay. And what I have now is x sub 1, 1, 0, 1. Okay. So what does that look like? What faces have degree exactly 1, 1, 0, 1? It's basically the triangle, but it's missing the 3 vertices. Yeah. So it's basically the 3 edges get label 1, 1, 0, 1. The triangle gets label 1, 1, 0, 1. But the problem is that the vertices don't. So I have to throw them out. Okay? So maybe let me denote that by just putting a little holes here to indicate that the vertices are not in x sub equal to 1, 1, 0, 1. Okay? Because basically what this is this minus this, right? By definition. These are the things less than or equal to 1, 1, 0, 1. These are the things less than 1, 1, 0, 1. So the difference is the things that have label 1, 1, 0, 1. Okay? So the problem is that what I wrote there is kind of morally true, but the issue is that I can't define the homology of something that is not a polyhedral complex. And this is not a polyhedral complex because the edge is in it, but the vertices are not in it. A property of the polyhedral complex is that if you take any one of your polyhedra, then all of its faces have to be in the complex. And that's not the case here. Okay? So I have to somehow adjust that statement to take this into account. And then, so the issue is that this is not a polyhedral complex. This is kind of the thing to be careful about here. But it is true that it is the difference between two polyhedral complexes. It's the difference between this polyhedral complex and this polyhedral complex. And what I morally want to say, again, we have to turn these things into theorems, but what I want to say is basically that, you know, if this thing is equal to this minus this, and this thing has no homology, then basically these guys are supposed to have the same homology to make up for it. Okay? And so, again, the point is this doesn't make sense. We don't have an actual definition of what this means yet, but I kind of want to say that it should be just inherited from here. Okay? And then I will say, okay, well, then this is equal to this, and I'll have a theorem. Okay? So how do I make this precise? Well, the way that I make this precise is, I think it's very nice, and it goes like this. So let's see, what's a good way to do this? This thing is a polyhedral complex, so it has a chain complex associated to it. Okay. So let me write this out by saying that, so let C like this be the chain complex of this simplicial complex. Okay. So what is C star? C star is a big sequence, right? It goes d-dimensional faces, go to d minus one-dimensional faces, etc. Okay, it's a long sequence, and then I'll write the same thing for the chain complex of this, which is also a simplicial complex, and then I'll write this for the chain complex that I'm trying to compute here. Okay? And so again, the point is that these guys are polyhedral complexes and this one is not. So what I want to do is this. I want to say that I have an exact sequence that looks like this. So what does this actually mean? So basically what I'm saying is that, I mean, each one of these C stars, again, is a whole sequence of arrows, right? Which, because I chose to write this horizontally, I'm going to think of writing these things vertically. Okay? So I'm supposed to think of this as d-dimensional faces go to d-1 dimensional faces, go to d-2 dimensional faces, and so on. Okay. And then what I'm saying is that, I mean, actually, I think I'm going to have to, let me actually write that out, what I'm saying. So what that picture actually means is that, let's look at this C dot x less than b. Okay, so basically this thing has some d-dimensional faces, then some d-1 dimensional faces, d-2 dimensional faces, and so on until 0. Okay, so this is what this guy is. Then next to it, I'm going to write this guy. Okay. So these are the d-dimensional faces of this thing, etc. And finally, I'm writing this guy, which looks like this. Okay. So this last column is the last column that we're trying to compute. Okay, so you should think that the last column that I have here is basically this top row. Right? It's the row of faces that have labels exactly equal to 1101. Okay? And then I make this column for the things that have labels less than or equal to b, and this column for the things that have labels less than b. And now, I'm writing this, right? 0 goes to this, goes to this, goes to this, goes to 0. So what do I mean when I write that? I'm going to have to put a bunch of arrows in this picture. Okay. Looks like this. I get basically this whole grid of homomorphisms. Now, what are the homomorphisms here? Well, the vertical homomorphisms, again, are just the boundary maps, right? From d-dimensional faces to d-1 dimensional faces. And what are these guys? What are, for example, how do you map a face here into a face here? Well, this is a face that has label less than b, and so that lives here naturally. Okay? And so you can just map it by inclusion. This is a subset of this. So what's the image? Sorry, what's the image? The image is the things that don't have label b, right? And now what's the map from here to here? What I'm going to do is that I'm going to take the faces that have label equal to b and just send them to here. And the faces that don't have label equal to b, that have a smaller label, I send them to 0. Okay? So what does that mean? What's the kernel of this map? Well, I killed everything that has label less than b. And that kernel is exactly this image. And so that's why along each row of this thing I have an exact sequence. So it's like a sequence of exact sequences. So that's the first thing I mean. Every row is an exact sequence. Okay. And then there's another thing I mean by this, which kind of a general construction that whenever you have we say that each square like this commutes. Every square that you see in that picture commutes. And what do I mean by this? The thing is that if you have an element of A, then you have two ways of getting an element of C. One is by applying the function that sends you to B, and then the function that sends you to C. Another one is by applying the function that sends you to D, and then to C. So maybe I'll call these F, G, H, I. And what should be the case is that if you take the composition of F and G, you should get the composition of I and H. So that's what it means to commute, and if you read out what that means here, you'll see that it holds very easily. Okay? So this is what I mean by having an exact sequence of chain complexes. Okay? And then what I do is that I invoke a theorem. And the theorem basically says what I was kind of hand-waving about. It basically says that if you have three chain complexes that are related by an exact sequence, then their homologies are very closely related to each other. And the way we say this is that this gives a long exact sequence of homology that looks like this. It looks like the I-dimensional homology of the middle guy goes to the I-dimensional homology of the right guy, goes to the I-1 dimensional homology of the left guy, goes to the I-dimensional homology of the middle guy, etc. Okay. So basically, what this says is that at each point of this grid, you have a homology that tells you, are you exact at this point or not? And I mean exact vertically, right? Because we're looking, we know that we are exact horizontally. Okay? But at each point, we have a homology group. Okay? And what I'm saying over here is that whenever you have a chain complex like this, then it's a fact that you get for free a long exact sequence of homologies that tells you that you can go from this homology to 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 this homology all the way down. Okay? This is a theorem, of course. This is not something you should just see right away. And I actually wrote up a sketch of the proof of this theorem on the notes. But what I want to focus on is actually showing you how we can conclude from here. And now I can erase this stuff. And I can basically say the following. Maybe I'll call this A, B, C. Okay. And you see what I want to prove is that, well, let me just prove it. So okay. So first of all, we said that this thing is acyclic. Right? And what that means is that this thing is equal to 0, and this thing is equal to 0, because x sub less than or equal to b has no homology. Okay. And so then I'll just make this computation that this homology right here is the kernel of C, because I'm mapping to 0, so everything has to be in my kernel. Okay. Now, this is supposed to be an exact sequence, which means that the kernel of C has to be the image of B. Then we say, okay, well, we have the first isomorphism theorem that tells us that the image of a map is equal to where we're coming from mod the kernel of our map. Right? But now, what's the kernel of A? Well, A starts at 0, right? So the kernel of A must be 0 because there's nothing here to be in the kernel except for 0. So we get the homology of XB. And so what I proved to you is that the I-dimensional homology of this thing XB, which we said was not a polyhedral complex, is equal to the honest I minus first dimensional homology of this actual polyhedral complex, X less than B. So we don't have to resort to this fictional polyhedral complex. We can just work with this one, which actually is a polyhedral complex. Okay. So that's the sketch, right? And of course, as you can see, this relies on some heavier machinery than we have used so far. So this diagram that I drew there is kind of the beginnings of what's called homological algebra. So, for example, if any